If intelligent aliens exist somewhere in this galaxy, the physics of the universe may guarantee that they can never reach Earth. Not because they lack the will, not because they lack the intelligence. Because the distances between stars are so absurdly, unreasonably large that crossing them requires more energy than most civilizations could ever produce, the speed of light is not a suggestion, it is a wall. And everything we know about physics says that wall cannot be broken. This is not a question about whether aliens exist. There are roughly 200 billion stars in the Milky Way. NASA's exoplanet surveys suggest that at least 20% of Sun-like stars host an Earth-sized planet in the habitable zone. That is billions of potentially habitable worlds. Some orbit stars billions of years older than the Sun, meaning any civilizations that arose on them had an enormous head start. And yet nobody has come. Nobody has signaled. In 1950, the physicist Enrico Fermi sat at lunch with colleagues at Los Alamos National Laboratory and asked a question that still has no answer. Where is everybody? One possibility is that interstellar travel is simply not possible, not impractical, not unlikely, physically impossible for any civilization, no matter how advanced. And the reasons are not exotic. They are basic: energy, time, and the structure of space itself. The nearest star to the Sun is Proxima Centauri. It is 4.24 light-years away. That number sounds manageable until you convert it into a distance your body can feel. 1 light-year is roughly 5.88 trillion miles. Proxima Centauri is about 25 trillion miles from Earth. Voyager 1. The fastest object humanity has ever launched on a sustained trajectory travels at roughly 38,000 miles per hour. At that speed, it would take approximately 73,000 years to reach Proxima Centauri. That is longer than all of recorded human civilization. And Proxima Centauri is the nearest star. The galaxy is 100,000 light-years across. If the Sun were the size of a basketball sitting in New York City, Proxima Centauri would be another basketball in Hawaii. The space between them would be empty. These distances are not a technical problem. They are a structural feature of the universe. Stars are not placed close together. They are separated by voids so vast that light itself, the fastest thing permitted by physics, takes years to cross them. Any alien civilization faces this same geometry. Their nearest neighbor is years away at light speed, decades away at any plausible fraction of light speed, millennia away at the speeds we currently achieve. But speed is not the real problem. The real problem is what it costs to go fast. And the cost is not measured in money, it is measured in energy. The kind of energy that makes the problem look permanent. Special relativity, published by Albert Einstein in 1905, establishes that nothing with mass can reach the speed of light. As an object accelerates toward light speed, its relativistic mass increases. The faster it goes, the more energy is required to accelerate it further. At 90% of light speed, the energy required is already enormous. At 99%, it is vastly worse. At 100%, it is infinite. This is not a technological limitation. It is a law of physics. No material, no engine, no fuel source changes this. The speed of light is the universe's hard ceiling. To understand what this means in practice, consider a modest scenario. A spacecraft with the mass of a large car, roughly 2,000 kilograms, accelerating to just 10% of the speed of light. At that velocity, the trip to Proxima Centauri would take about 42 years. Still a human lifetime, but conceivable. The kinetic energy required to accelerate 2,000 kilograms to 10% of light speed is approximately 9 times 10 to the 17th joules. That is roughly the total energy output of a large nuclear power plant running continuously for 30 years for a single small spacecraft. No crew, no life support, no deceleration fuel. A crewed vessel would need life support, radiation, shielding, food, water, and enough fuel to decelerate at the destination. Realistic estimates put the required mass at tens of thousands of tons. The energy required to accelerate that mass to even a modest fraction of light speed exceeds the total annual energy consumption of human civilization by orders of magnitude. The rocket equation makes this worse. Any rocket must carry its own fuel, and the fuel has mass, which requires more fuel, which has more mass. This exponential penalty means that for high-velocity missions, the fuel-to-payload ratio becomes absurd. Fusion propulsion improves the numbers. Antimatter propulsion improves them further. But even antimatter presents devastating problems. The total amount ever produced on Earth, across all particle accelerators combined, is roughly 20 nanograms. Storing it requires magnetic containment so it never touches normal matter. Scaling that to the tons required for an interstellar mission is not an engineering challenge. It is a fantasy. Any alien civilization faces these same equations. The physics does not change on the other side of the galaxy. Einstein's laws apply everywhere. The energy wall is universal. Assume, for a moment, that an alien civilization solves the energy problem. Assume they build a spacecraft capable of sustaining 10% of light speed for decades. What do they face? A one-way trip to the nearest star takes 42 years. A round trip takes 84. If the target is a star 50 light-years away, still inside our immediate stellar neighborhood, the trip takes 500 years each way. 1,000 years round trip, no individual lives that long. The concept of a generation ship, a vessel large enough to sustain a breeding population for centuries, introduces problems of social collapse, genetic bottleneck, and mechanical failure over timescales no machine has ever been tested against. Relativistic time dilation offers a partial escape. At 90% of light speed, time aboard the ship passes at roughly 44% of the rate experienced by those left behind. A 100 light-year trip would take about 111 years in the home civilization's frame, but only 49 years for the crew. This helps, but the crew still ages 49 years. The civilization they left behind moves on by 111. Communication with home becomes increasingly delayed and eventually meaningless. And 90% of light speed is not a realistic target. Even a civilization harnessing all the power of its home star would be dedicating a significant fraction of a stellar energy budget to send a single ship on a single voyage. The result is a kind of temporal prison. Even if you can cross interstellar distances, the time required isolates you from everything you left behind. You arrive in a future that does not remember you. You cannot return to the present you departed. Interstellar travel, even when it works, is a form of exile. The space between stars is not empty. It is filled with gas, dust, and high-energy particles. At relativistic speeds, these become lethal. A grain of dust massing 1 milligram, stationary in the interstellar medium, would impact a spacecraft traveling at 10% of light speed with the kinetic energy of a small bomb. At 50% of light speed, the energy scales dramatically. At 90%, a single dust grain carries the kinetic energy of several tons of TNT. The interstellar medium contains roughly 1 hydrogen atom per cubic centimeter. At relativistic speeds, those atoms become a continuous stream of radiation striking the forward surface of the spacecraft. At 50% of light speed, the energy of each incoming proton is in the range of hundreds of MeV. That is not weather. That is a particle accelerator aimed at your hull. Shielding against this requires mass. Mass requires more fuel. More fuel requires more energy. The problem compounds. Robert Bossard proposed a solution in 1960, the interstellar ramjet, which would scoop hydrogen from the interstellar medium and use it as fusion fuel. In practice, a 2021 analysis by Peter Schatzschneider at the Vienna Institute of Technology showed that the magnetic funnel required would need to be absurdly large, and the drag from scooping material at high speed would partially cancel the thrust. The ramjet is physically feasible, but practically useless. Any alien species attempting interstellar travel faces the same interstellar medium, the same dust, the same radiation. The hazards are built into the structure of the galaxy. In 1961, astronomer Frank Drake wrote an equation to estimate the number of detectable civilizations in the Milky Way. The Drake equation multiplied factors, including the rate of star formation, the fraction of stars with planets, the fraction of planets that develop life, the fraction that develop intelligence, and the length of time a civilization remains detectable. The equation was never meant to produce a single answer. It was meant to organize our ignorance. But even conservative estimates, using the most pessimistic values for each variable, tend to produce numbers greater than 1. The galaxy should contain at least a few civilizations capable of signaling their existence. We have been listening since 1960, when Drake himself pointed a radio telescope at 2 nearby stars in Project Ozma. SETI has been running in various forms for over 65 years. The Breakthrough Listen initiative, funded by Yuri Milner in 2015 with $100 million, surveyed 1 million nearby stars and 100 nearby galaxies using the Green Bank telescope and the Parkes telescope in Australia. Nothing, no signal, no pattern, no repeating structure in any frequency band that cannot be explained by natural phenomena. In 2020, a candidate signal from the direction of Proxima Centauri, designated BLC-1, briefly excited researchers at Breakthrough Listen before being identified as terrestrial radio interference. 65 years of listening, and the silence is total. This silence has a name. It is sometimes called the Great Silence, and it weighs more than any single discovery in the history of astronomy, because it is not the absence of data. It is data. The silence tells us something. The question is, what? Robin Hanson, an economist at George Mason University, proposed in 1998 that this silence implies the existence of what he called the Great Filter. Somewhere between the emergence of life and the development of an interstellar civilization, something stops almost every species. The filter could be behind us, in which case complex life is far rarer than we assume, or it could be ahead of us, in which case civilizations tend to destroy themselves before they reach the stars. If intelligent aliens exist in this galaxy, and the numbers suggest they probably do, then they are almost certainly trapped. The same way we are trapped. By the geometry of the universe, by the speed of light, by the energy costs of acceleration, by the time required to cross even the shortest interstellar distances, and by the hazards that fill the space between stars. This does not mean the galaxy is dead. It means the galaxy may be full of life that can never meet. Civilizations separated by dozens or hundreds of light years, each one looking up at the same sky. each one asking the same question Fermi asked in 1950, where is everybody? The answer may be the simplest and most unsettling one available. Everybody is home. Everybody has always been home. Because the universe is not built for travel, it is built for distance. You can step outside tonight and look at the stars. Every one of them is a sun. Some of them are circled by worlds not so different from this one. On some of those worlds, right now, something may be looking back at your star and wondering the same thing you are wondering. Why has nobody come? The answer may be that nobody can, that the distances between stars are not problems to be solved, but boundaries to be accepted. That the universe gave life the ability to wonder about its neighbors and then place those neighbors permanently out of reach. And distance, at the scale of stars, may be permanent.